So in this video, we're now going to use the knowledge we have about how channels behave to develop what I'm going to call a basic channel model that applies both to wireless and wireline situations. As we know, interference and noise are going to be a problem with wireless channels, not so much with wireline channels. That makes, from a communications engineering viewpoint, wireline channels are fairly boring. They don't have much interest or design flexibility. Whereas in wireless channels, because of the interference and the noise, makes it a much more challenging and interesting problem. I'm going to give an example of how to apply this model of channels to what's called baseband communication, which is perhaps the simplest kind of communication possible. Baseband basically means you send the message directly. But let's develop that basic channel model. And as you know, this is our block diagram model of communications. And we're concentrating, of course, on the channel. And what we've seen, that for both wireless and wireline situations, this is a very good model for the channel. So what I'm doing is I'm putting the channel in a box, has X of t coming from the transmitter in, and what we call R of t, the received signal coming out of the channel. It is delayed. The transmitted signal is delayed by some amount in both situations. It may be attenuated. Alpha is supposed to represent a gain, but usually alpha is less than 1, and certainly, hopefully, greater than 0. For the wireline channel, basically alpha is 1, but for the wireless channel, it can be significantly small. It can be a very small number indeed. Then to that are added the interference, which usually comes from man-made sources, and noise, which is ubiquitous. So a simple relationship between input and output is given by this expression. And we're going to use this in our considerations of communication channels and systems. So for a wireline channel, to summarize, the delay tau is given by the distance between the transmitter and receiver divided by the speed of propagation, which, as I said, is a fraction of the speed of light in free space. Alpha is basically 1, and the interference and noise are basically 0. So it makes it kind of uninteresting for us. But in wireless channels, situations get much more challenging. There is a delay, which in many situations can be small, but if you're talking about satellite communications or even ionospheric communications, that delay can become significant. What's much more important is the fact that the attenuation is inversely related to the distance between transmitter and receiver. Further away you are, the further away the receiver is from the transmitter, the smaller the signal you're going to receive. And who knows what kind of interference and what kind of noise are going to inhibit the reception of the signal. Now, we're going to basically assume that we can control the interference by filtering. Basically, as we're going to see as we go through, that in well-designed communication systems, the interference from other communication signals is going to be out of band. What that means is in a different bandwidth, range of frequencies than X will be. So we can, just by filtering, get rid of it. Noise is another problem. Noise we're going to consider as being wideband, technical term, which means it's everywhere. And it's going to be out of band, it's going to be in band, it's going to be in the same transmission bandwidth as we're using, and so we have to worry about it a lot. But two big effects are going to be the attenuation and the noise. So we need a way of describing noise in particular. This is going to be a new signal for us, has very interesting and special properties. We're going to use a model called white noise. The reason it's called white is because it has powered all frequencies just like white light has equal power more or less in all the range of colors. Put all the colors together, you get white. So it's called white noise because it has power at all frequencies. Random phase and amplitude. And here is an example of white noise that I simulated on a computer. And it's very erratic, very wiggly. Sometimes, if you look very carefully, it's not so wiggly. And sometimes it has these really big values. It's really a random signal. The one special properties that noise signals have is that when you add two noise signals together, their powers add, not their amplitudes. So we're going to see this in more detail in just a second, but this is a very important property of noise signals, not so much for regular, if you will, non-noise signals. Suppose you add together two sine waves of the same frequency. Well, their amplitudes more or less add, depends on their phase. But if they're in phase and at the same frequency, their amplitudes add. But their powers are, there's a greater power than just the sum of their powers individually. Not true for noise. For noise, the powers add. So, we need to talk about what's called the power spectrum, because communication analysis relies a lot on understanding where signals have power. And to make it convenient, we like to talk about power in the frequency domain through something called the power spectrum. And very simply, it is the magnitude squared of the Fourier transform of the signal. And that's what a power spectrum is. So the power spectrum for signal S is just this magnitude squared. Well, as we know, magnitude squared is S times S conjugate of F. But this, because of our properties, is just S of minus F. And so when you multiply these two things together mathematically, what you discover is that power spectra are always even functions. So this is going to be important a little bit later. So it's an even function. It's just a mirror image about the vertical axis. For all power spectra have this property. There are no exceptions. Okay. Now, the next thing to talk about is this power spectrum at the output of a filter. So we know that if we have a filter here, which has X going in, transfer function of capital H and Y coming out, that the Fourier transform of the output is equal to the transfer function times the Fourier transform of the input. Well, to find the power spectrum, we just need the magnitude squared. And the magnitude squared of a product is the product of the magnitude squareds. That's Py, that's Px, and we get that relationship. Pretty easy to see. Not very difficult to derive at all. Now, because of Parseval's theorem, if you recall Parseval's theorem, that said that the integral in time, which we call the power, is equal to the integral of the Fourier magnitude squared of the Fourier transform. Well, that's for us now the power spectrum. And because we now know that power spectra are even, the integral from minus infinity to infinity is just twice the integral from 0 to infinity. Because it's even, this integral is going to be the same as that integral. So it's a little bit simpler for calculational purposes. Just integrate over the positive frequency axis and multiply the answer by 2. And finally, I want to point out this little interesting result, that you can think about the power of a signal within a given frequency range as being the integral of the power spectrum over that frequency range. The reason that comes about is because of that result. So suppose capital H is a bandpass filter between F1 and F2. And so we know what that does is that the output Y only thing in the output is the frequency components of the input in that frequency range. Well, the power in the output is just given by the integral. And so when it is a bandpass filter like this, magnitude of h of f squared is just 1 within the frequency range, and that integral simplifies to that. So you can interpret this bandpass filtering to be, I'm only measuring the power in the input signal over a given frequency range. So once you have the power spectrum for a signal, you can figure out how much power it has in different ranges of frequencies simply by integrating over that frequency range. Very useful for us, as you're going to see in a second, especially when we talk about noise. So, going back to white noise, as we said, by definition, white noise signals have a constant power spectrum. So their power spectrum is in some sense the easiest, it's just a constant. And the amplitude of the constant, it turns out, is n naught over 2, and we'll see why there's this over 2 factor in just a second. Now, what's the power in white noise? It's supposed to be the integral of the power spectrum. What do you get for the power in white noise? Of course, the answer is it's infinite. So, white noise is a fiction. It doesn't exist in the real world, but it's a very convenient fiction. Very useful for us in analyzing communications problems. And believe it or not, we're going to assume that in channels, the channel adds white noise, infinite power noise, to our signal. It's going to turn out it's easy to remove that noise because of filtering. So, again, the power in the noise signal within a given frequency range is just going to be given by that, the spectral, so-called spectral height, times the bandwidth, the range of frequencies of interest. And that's called bandwidth. So the bandwidth is f2 minus f1. So, again, using our result that we shown in the previous slide, the power spectrum of the output of a linear filter, when white noise serves as the input, is n naught over 2, the power spectrum of the input times the magnitude of h of f squared. So, in most situations, when you have some sort of filter like this, the power of the output of that filter is now finite, even though the power coming in is infinite. So this is a convenient way of modeling noise having any kind of spectral properties at all, is that you pass it through the appropriate kind of filter. So the beginnings, though, start with white noise because it's very, very easy to deal with. Now, in analyzing communication systems, the bottom line measure of quality is the signal-to-noise ratio. So the idea is that we're going to wind up, in almost all cases, with a signal plus noise. Our final signal that we receive after going through the receiver is going to be a signal-related component and a noise-related component. We want a measure of quality of how big the signal is relative to the noise, and the signal-to-noise ratio is the standard measure. It's the power in the signal part divided by the power in the noise part. And clearly, the bigger the SNR, the better quality it is, the smaller the noise is, if you will. Well, given by what we've seen in terms of power spectra, it's the ratio of these two quantities. Power in the signal is given by that, and the power in the noise is given by that. And also, as we've seen, SNR is frequently expressed in decibels, in dB. So, here's the general lay of the land in terms of our channel model. The channel introduces a delay, it attenuates, adds interference and noise. Like I said, we're basically going to assume the interference is not there, And that gives us the final expression for the signal-to-noise ratio coming out of the channel as being this quantity shown here. So certainly the effects of attenuation in the channel really hurt the numerator. That can make it small in the wireless situation. As you get further and further away from the transmitter, this number gets smaller and smaller and smaller. So the SNR goes down like the square of that attenuation factor. And the noise part depends, of course, on the spectral height, but also depends on the bandwidth over which X exists. So I'm assuming that X is some signal in the frequency domain, which exists from frequency FL, a lower frequency, to some upper frequency. And the only thing we need to consider is what's called the in-band noise. I'm about to show you how that works. So let's talk about the design of a transmitter and receiver for a channel. So we have now our channel model, and now we know what the characteristics of the channel are. What we're going to do, for all kinds of reasons, is simply transmit the message as it is. The transmitter is going to provide some gain. Usually the gain is much bigger than 1. Provide some power to the signal, but it's just going to send it as it is. Most message signals have a low-pass spectrum. Their support for their frequency, their Fourier transforms, usually goes from 0 frequency up to some upper frequency. For speech, it goes up to like 6 or 7 kilohertz. Audio, music has a somewhat higher frequency range, but still it's a low-pass spectrum. So given that's the way we're going to do it, we're hopefully going to look at the channel model, and the transmitter design is going to be determined by how we think we're going to send it and the characteristics of channel in that frequency range. Well, as we know, baseband communication does not work well for wireless channels. They just, low-pass signals do not propagate very well for wireless channels. So it's rarely, if ever, used for wireless channels. For wireline, there is also an attenuation, as we've seen. Only in the high frequency limit do we get no attenuation. So it is used, though, for wireline channels for communication over limited distances. That is definitely the case. So let's see if we can figure out, the goal is going to be to figure out a receiver that goes with this transmitter and to figure out the signal-to-noise ratio in the recovered message. All right, so here's what's coming out of the receiver, out of the channel rather, in the frequency domain. So I'm assuming, like I always do, that my message signal has this triangular spectrum, just a habit of mine, just to use a triangular looking spectrum. So it has the highest frequency of W. It has a bandwidth of W. The so-called bandwidth is equal to W. And again, bandwidth is defined to be that portion of the positive frequency axis over which the signal is non-zero. So there's our good old message signal, M of F. It's contained in white noise, which is very broadband. I showed this as a blue thing. It's everywhere. Well, clearly, if I was to use that as my demodulated message, if I use that to send that to the sink, the signal-to-noise ratio would be 0, because white noise has infinite power. It's very clear we don't need this portion of the noise. Why keep it? It's not what we call in band. In the band width, in the frequency band of the message. So in most receivers, the first thing they do is remove what's called out-of-band noise. It's out of the bandwidth of the transmitted signal. So in this case, since we're doing baseband, we low-pass filter. This is called front-end filtering. Virtually every receiver in the communications world, the first thing it does to the signal coming out of the channel is low-pass filter. In the baseband communications situation, that is going to be our message signal. It's going to be reconstructed. So now the message in the frequency domain looks like this bandpass signal. You have the message part, the transmitted message comes through without being altered by the low-pass filter, but the noise is certainly cut down. Now, what is the signal-to-noise ratio? It's going to be the attenuation squared introduced by the channel times the gain squared of our transmitter times the power in the message, whatever that is, divided by N0 W. N0 times the bandwidth of the noise, which is just W. So you can see that the transmitter is here, has a gain to try to fight the attenuation introduced by the channel, basically. The bigger the noise is in the channel, the smaller the SNR. I think that's pretty obvious. I wouldn't worry too much about bandwidth here, because the power in the message will probably change if you change its bandwidth. This part of the SNR basically could be a constant for most situations. May or may not be, but I would not say that the wider the bandwidth, the smaller the SNR has to be. That certainly is not true. Now, another thing I want to point out is those of you who know what's going on will know that M hat, the signal part of M hat, is equal to alpha times G times the message plus filtered noise, which I'll just call N tilde. So don't we need to worry about alpha times G? And in many situations, we do not demand that be 1. This corresponds to the knob on the radio, a volume control, if you will. We'll make up for it by amplification a little bit later. But if you amplify this entire signal, multiply it by a constant, you do not change the SNR. So we can study the SNR for this signal as it is, and that will be sufficient to characterize quality. And we will fix the gain problem, if you will, by further amplification. So we now have designed for ourselves a communication system. The model that we've developed for just the channel describes the delay, the attenuation, the interference, and the noise that the channels add. Like I said, nothing good happens in a channel. Signals don't get bigger, and they get delayed, sometimes attenuated by a lot, especially in the wireless situation. Interference gets added, who knows what it is, depends on the situation, and the noise is always prevalent. Question mark means you don't know really how big it's going to be in any given situation. You have to do the best you can. To combat the presence of the noise and the interference, for that matter, most receivers for wireless consist of a front-end filter to remove out-of-band noise and out-of-band interference. And again, out-of-band means not in the bandwidth of the transmitter signal, not in the bandwidth of X. Why keep the noise and any other signals floating around that are out of band when a band pass, maybe a low pass filter for the baseband situation, a band pass filter for modulated situations, can get rid of all other signals. So that's why most wireless receivers, right at the front, there's a filter. And then further processing goes on in many cases to yield the reconstructed message. We'll talk about those kind of situations in succeeding videos.